The first speaker in the session is Prem J. Raman, and he is actually the only Australian on our today's program. So, he is, I actually don't know how to pronounce it, it's Swinburne?
Yes.
So it's Swinburne University, but the talk will be about the work done with an Australian meat processing company.
Thank you. I've got this one. This still works, right? Thanks, Daria, and thanks again for accepting my proposal and giving this opportunity. I'm the only local presenter. I'm from a university called Swinburne University of Technology. Its place is in Melbourne. It's about 10 minutes by train from where we are here. I'm a senior lecturer, so I'm also the only academic who's presenting today. Or I know some of you have dual affiliations with university, but mostly have your home in the industry. I'm the other way around. I have my home in the university, but all my work has been with industry. And also the topic is going to be a bit off a traditional search, but it's still going to be applications of machine learning or into the data science area, but this is under the Internet of Things, which is my research area. Just a bit of a background for some of you who may know this area, for others who not. I work in what's called the Industry 4.0. This is a term that came out from Siemens, from Germany, but now it's sort of taken over by pretty much any big manufacturing and automobile companies, and they're trying to build this into what from 1.0 all the way to what we are now at 4.0. And this is sort of very relevant to all the talks that you heard previously. This is thanks to digital data, really sort of getting data from every source, whether it comes from Alexa or it comes from Bing, and then using this in order to produce more effective products that we are currently using. The example that I normally give in this scenario is, what if you can go online and order your shoes from Adidas with your name printed on the sole, and all this is done by machines talking to each other. There's no humans in between, right? That's kind of what Industry 4.0. We are still in the automation area, where you need someone to go program the machines, tell it that that's the sole, that's the color, you need to do that, and the machine starts to paint it. How do we then start connecting all this together? What are all the sort of technology pillars under this? You're probably familiar with everything. My area is more around the Internet of Things. This is about not just sensors, about your wearables, your smartphones, could be social media, data sources that are in digital form that we can use to generate any sort of insights in order to deliver an Industry 4.0 solution. So that leads me to what is called the Industrial Internet of Things, which is one of the key pillars of Industry 4.0. I just picked this up because why is this very important? These are just numbers of how data from sensors, if it could be used to produce 1% optimization, that could lead to about $30 billion worth of fuel saved. In agriculture sector, it's about $2 billion. Now, I'm sure you're all probably familiar about smart agriculture, putting sensors on the field, understanding how the crop grows, identifying when to harvest. That's the age we are in, right? Yes, we have farmers, and they are the best who have the experience, but these are technologies that are helping them to actually do these things much better, more effective, thanks to changes in climate, in a whole other factors. So technically, most organizations today have IoT as a part of the strategy, and I'm sure that most people here who are from the industry, your company has a vertical IoT that you are either working with, collaborating with, or they're at least talking about it. So in my view, some of the components of this, when we say IoT, the most common thing that comes to everyone's mind is the sensors. But having worked with industry, what I found out is when you want to have IoT or Industry 4.0, people and processes are very important. Now, people coming from search or from web searches, you all look for your users. For me, from manufacturing point of view, people determine the processes of how to produce something. So before I do the cool machine learning and building models, I first need to understand the context of how this data is being produced. How do I fit the data? Most people, when I say most industries in Australia, when they come to us, the first thing that they say is, I have collected a lot of data. Can you guys, with some smarts, try to do some analysis for us. Then we go to look at the data and we say, unfortunately, half the data you have collected is useless because you've just been collecting data. We do not know how to use it. We had to go back to the fundamentals that what does the data mean for you? What are the business problems where people are connected? Then comes the technology factor. So I kind of use this slide to motivate the fact that IoT is not just about get some sensors, put it in the plant, collect data, do some analysis, you can result. That's not IoT. That's one notion of it. Clearly, it doesn't work in a real world in industry. So sort of the person in between all this acquiring data and aggregation. Now, this was a study done by Cisco with Black & Decker in the US. And when they went into the manufacturing plant and they started looking at saying what are the 4 top important things, as you can see, the actual things or the sensors are the least. Now, before working for Swinburne, I used to work for a company called CSIRO, which is Australia's premier research agency like the NSF. They used to manufacture sensors about 6 years back for agriculture. A sensor used to cost about $2,500. Today, you can buy them off eBay for about $50. That's how fast the technology has grown, thanks to Moore's law, right? So, but these parts have not really changed a lot. They're still the same. That brings me to the actual work that we did. This work was funded by AMPC, the Australia Meat Processing Corporation. This is a research development corporation funded by its members. So there are about 20 different meat processing producers in Australia. They are end-to-end. What I mean by that is some of them own the farm, so they actually grow meat. And by the way, for vegetarians, yes, there's going to be some meat stuff here, so apologies, but no blood, okay? And they kind of foresee what kind of research activities that they need to conduct in order to improve the industry, provide better value. Most of the money that they get in goes into more pure science. What kind of new breed I can grow, what kind of food I can deliver them. This project came out because they wanted to look for an industrial IoT solution in a meat processing plant. Acknowledging this was sort of led by one of the IoT lab directors in Swinburne, by Professor Dimitrios, and my other team members. So we sort of took the idea of identifying what are the opportunities. And the approach we took was very consultative. We spoke to about 10 different meat processing producers in Australia, right, from Brisbane, Adelaide, Sydney, and Victoria, right? And through that, we kind of went into a meat processing plant, and through consultations, we identified quite a few things. So that's how a meat processing plant looks like, right? Now, yeah, that's a very, I don't know how clear. I've got a real photo of it later on. But that's the level of automation they have. The best tool that they actually use is a knife, right? So that's a conveyor belt, and you've got meat going along. Someone takes it off onto a processing place, cuts it, slices it, removes fat, does whatever it is, and then produces a product which then goes into packing, which you actually go to your supermarket and buy, right? Now, that's a very different experience to shopping in a supermarket, right? So you get it very nice and packed. This is exactly what. Now, they do have some automation technologies, things that can cut the actual carcass into different pieces based on an X-ray scan, right? But then the real stuff about producing the product, it's all manual. So we were given the task of, given a scenario like this, the only KPIs they actually have is, I have carcasses coming in, I have products going out. Now, no one knows what's happening in between, which means today, I need to produce 500 pieces of rump steak. I need to process 1,000 pieces of carcass in order to produce that. My supervisor goes to each of these workers and says, you need to do this, get the meat, start doing it. If they don't finish work on time, let's do another extra 1 hour of shift, or let's pass the shift on to the next person. And in this industry, it takes about 2 weeks for them to go back and look at any data to see if they were even meeting the quality standards. And that is one person going to 10 different machines, collecting data, putting in an Excel sheet, and doing some analysis, right? And that's only the quality aspects of it. So we looked at this from a combination of consultation, our expertise in IoT, and also a bit on data science, and sort of identified a few opportunities. One was we challenged ourselves thinking, can we determine some sort of fine-grained KPIs? Rather than saying what goes in and what goes out, can we find out a bit more of who's doing what in between, right? Some of the other activities that some of you would have been aware of is what's called a farm to fork. Let's example, go to your supermarket, buy a piece of meat, scan it on your phone. It says exactly where the meat came from, which cow or whatever it is it came from, which farm, which location, what did it eat, ... And this is getting very important these days. You'll see work in traceability along blockchain. You'll see work on traceability thanks to various sort of disease that could get across and people could die because of that. Melbourne, for example, in Australia, about a year back, we had a big problem with sallow, I think it was a fish-based infection that actually resulted in some people dying. So our work was we looked at this key aspect of how do we use some sort of IoT technology to understand or provide a more fine-grained KPI. So the solution we came up was the only tool that our operators in the industry use is knife. So one guy came up and said, can you figure out if the knife is sharp or not? And that's very important for them because if you use a blunt knife, have you ever, any of you cook here, have you ever tried cutting a tomato with a blunt knife? If not, go home and try, right? Just blunt it off and try cutting it. You can actually hurt yourself if you're doing that for 6 hours, right? So one metric is it sharp? So we started off with that approach, but we kind of ended up with a different objective. But the only tool we had was a knife. So we were saying, okay, how could we assess a worker's performance by the movement of the knife, right? So our system, we don't produce sensors, so we use off-the-shelf technologies, right? So the sensors that we used, we bought this from the US from a company called MetaWare. It's about $50 US. Proximity sensors, again, Raspberry Pis, everything off the shelf. We sort of built our own architecture where a worker wears this like an activity device on both the hands, goes on cutting meat. We then use that to determine activity. So from a ML problem, it's recognizing activities, but not somebody walking or sleeping, using knife to cut a piece of meat. So this, you probably have seen much better diagrams of the architecture. It's very straightforward. So we conducted a real trial to validate our study. Given its research, university, limited budget, we could not go on for weeks of trial and everything. This was about 2 days. This, what you see up here, this was done in a more controlled trial. So this is a master butcher. In this, we had the liberty of giving the butcher a blunt knife. So we could actually see how the accelerometer data or the gyroscope data would actually differ from a sharp and a blunt knife. And we have statistical evidence that they're really different, right? But then when we went to the plant, it's a live production plant. They've got KPIs to meet. We can't give them a blunt knife because it's going to produce bad quality meat. And then we also found out that when we did this pre-trial, this guy was actually slicing meat. When we went to a real environment, they were actually removing fat. It was a totally different operation, something like this to something like this. So based on this, we sort of had this on 4 workers over 2 days across 4 different shifts, close to about 8 hours of data per day, about 16 hours of data that we're able to capture. Then we started building our models. I'll probably quickly show you a video just to make sure if it's muted. That's good, okay. So this is one activity called alignment, and all this is done by the person wearing this watch just under the glove there, while this person is doing a productive activity, which is, as you can see, removing fat from the meat, while this person is now idle. Now, he'll actually put it back in, and I'll tell you why later on. And this person will pick it up. Right. Now, so what the outcomes are. The one on the left that you saw, that person is a more experienced worker. The one on the right was experienced, the left was an inexperienced worker, a trainee. And that's exactly why the bigger piece of meat was given to the more experienced person, because he might be wasting it. Now, the outcome of this, you can see here, this was for 1 hour of data that we sort of wanted to visualize what it was. The experienced person was actually only working 60% of the time. And they actually end up producing, now I call this active states because if you look at a typical ML, you've got these 3 states, we count how many times they are being productive. He produces about 49 pieces of meat at almost half the time of what this person, working for almost 90% of the time, producing about 30 pieces of meat. Now there's one aspect here that requires a bit more technology, which we're now trying to do another trial with them, the quality of the output, right? This is only the speed at which they're doing, it's called throughput. It doesn't mean the quality is always high. But what this essentially means is this person has a much higher risk of being injured, because it could be that he's sort of really putting a lot of effort when he's working for almost 90% of the time. And hence, this industry, for example, cost of injuries to wrists and to the muscles around is around $100,000, right? So, and the most important thing is they want to help them with better training, right? Take them off the plant and give them more training. Another big outcome that we had was, until then, we did the project, they actually had no insight of such data at all. All they knew was something comes in, something goes out. Now with this, you can imagine if it's a conveyor belt, your line is only as fast as the slowest person on the line, right? Which means you can now reorder your workers to have much higher productivity. Now we did a quick payback based on off-the-shelf hardware. We are not into the commercial stream because we are a university. But we had another company who partnered with us, and they did some quick work. And in terms of throughput improvement, if we are able to reach around 25%, it's half a year payback. And this was for a factory which had about 400 people. So it was costed for about 400 people, having the watches, the infrastructure installed, and also some sort of software being developed for them and maintained for about 3 years. Now, now that the other part is done, because we're academics and we had access to data and some video, what we ended up doing was we thought, okay, we've got 3 activities that we classified from the project point of view. Could we actually go and identify more number of activities with the same data? And so we went to a set of about 7 different activities, from slicing, cutting, pulling, reaching, and feeling. Now, this is sort of our own definitions of some of this, which we verified with what the industry uses to define some of these activities, right? So we then used this sort of a representation of how the data look like with each of those activities. So we could clearly see sort of a big difference. And we used stock SVM models, about 43 features from acceleration, 32 from gyroscope, anything from mean standard deviation to acceleration. And in some cases, we considered scenarios where the worker actually had the watch on both the hands. So we consider both the working hand as well as the other hand, because in some cases, when they're holding the meat, this hand is more still, so it increases the accuracy of the overall solution. And we also tested this on creating different SVM models. Stock SVM, we did not upgrade the model. Train it per worker, train it across workers. So pick a sample from each worker and do a cross-model verification as well. And I guess that sort of gives us, with 3 activities, because it's far more easier with this activity, we were about 90% accurate in determining what was actually happening in the scenario. But then when we started going in depth of trying to determine 7 different activities, you could see we were around the 65–70% mark in terms of going to about 7 different activities. But again, when we went into this trial, we did not expect to have this many activities at all. So it was sort of really looking at the data. We kind of looked at it and said, okay, can we try doing something with it? And that's pretty much what we did. So it probably brings me about to the end of my talk. Thank you very much. Any questions and feedback? Yes.
Thanks for the interesting talk. I'm wondering if you have used the supervised approaches for your recognized activities, or if you use something semi-supervised or unsupervised.
It's all supervised. So we use SVMs. So we had to train it with all. So some of this data, we were able to collect video of the workers from the plant. So we used that to annotate all our data streams to prepare our training data set. And then we trained the SVM models. All we did was we trained the model with either trained from one worker and tried to determine all the activities of other workers, combine the data from multiple workers to create our training data set. So we tried these combinations, and that was the accuracy I showed you before. Yep.
So how did you get the label for the activities? Was it like manually inspect or like matching it with the video?
Matching it with the video and working with the domain expert from the industry who could tell us what was actually happening there.
So how much, like, can you give an estimate as to how much data you actually end up with label data?
Oh, we had almost, from the 2 days, close to about 20 hours of label data is what we had. Cool. Thank you very much.